Welcome back to this fourth installment of this series on the knapsack problem. And I'm writing here in parentheses this R.D. Littlewood-Polya rearrangement theorem, because what I'm going to write now is going to maybe remind you of that, and if not, we'll get back to it. It's a very important theorem in mathematics. Okay, so three big people coming together to write this rearrangement theorem. So we are switching to a continuous version. Okay, I wrote it like, okay, it's a knapsack problem, but continuous. Okay, so we are going to move to continuous case. So I'm going to formulate the problem and say something about how it is solved, and which will remind the greedy algorithm, but again, it's going to be a continuous version of what we saw in the previous videos. Okay, so we are going to choose a range, okay, t, or index of t, which will be the segment 0, 1. It's all normalization, okay, so let's make t go between 0 and 1. It's like time here, but it's not really t. Okay, and there is a return in every point of time. In every point in this segment, we are going to get r of t. Okay, that's the return. It's positive, okay, or non-negative at least. Great. And what I want is to, at each point of time, to choose a function x. Again, it's also going to be a function from defined on the segment 0, 1. And here is what I'm trying to maximize here. So my problem now is the following: maximize. Okay, and what I'm going to now have to choose is a function x. Okay, writing it like this to remind us that it's on the segment 0, 1. And we are going to look at the integral 0 to 1, and that's why we do this normalization. We need a finite segment to integrate over here in this problem. And what is the return? The total return here will be RT, the per period return, time xt, the intensity that we will choose at time t dt. Okay, so now it's a continuous version of what we saw before, and we still have the constraints here such that, okay, we can't set x to be equal to 1 all the time. The integral between 0 and 1 of xt is going to be less of dt, always important. It's going to be less or equal to some big number m. Okay, so remember the new representation that we had in the previous video. It's kind of have to remind you something from there, but it's the total integral of x that we can choose. Okay, so we cannot set x to be 1 all the time potentially if m is strictly smaller than 1. And another thing, of course, is that xt, okay, xt has to be bigger or equal than 0. And I'm being a little bit less careful. It's surely almost everywhere, but okay, almost everywhere. Let's write it like that. Okay. Okay, so that's the problem. Okay. So now what will be the solution for this problem? So it is possible to show, okay, that's the optimal solution. Let's call it x star. Okay, so optimal solution in this continuous version of the knapsack problem is going to be some x star of t. Okay, which will be the following. Okay, we are dividing it into 3 cases. Okay. Xt are actually going to choose it to be equal to 1 if RT at that point t, okay, is bigger than a certain threshold c. It's really bigger than c. We'll see what is that number. It's going to be equal to exactly 0 if RT is going to be strictly less than this constant c. And it's going to be some value delta t, which is between 0 and 1, for the case where RT is exactly equal to C. Okay? So if RT doesn't have any point or is just one point in which it's equal to exactly C, okay? It's strictly monotonically increasing, for example, or decreasing or something like that, then that will happen only in one point, and for the integration it doesn't matter. But if there is a plateau at some point at exactly the plateau is at height C, then yeah, I will have to take part of it. What is that C? C, the constant C is such that, okay, indeed, the integral of xt, okay, dt is less or equal than m, and if we can choose this, if this exists, then it can be exactly equal to m. That will be our x star. Okay, so what x star is saying, it's again, let's be greedy. That's what this optimal solution is saying. For the ranges of t in which RT is big enough, okay, get the bigger values, in this case higher than the constant c, take all of it. Okay, when R of t, the return is very low, meaning it's strictly less than c, don't touch it. Okay, set xt equal to 0. When it's exactly c, if you are allowed to take just part of that range on which RT is exactly equal to c, then you can take part of it. Okay, and the part, and then this is integral from 0 and 1, okay, is done such that the integral eventually will be actually equal to m. Okay, we want to achieve this take the most that we can. Okay, so if that is possible to take parts of that range, yeah, we'll take the parts that will exactly complement the amount of xt that we integrate over to be exactly equal to m. So how do we prove something like that? Again, there is the rearrangement or exchange, sorry, I'm saying rearrangement, but it's the exchange argument in which if you take two disjoint subsets of 0 and 1, okay, on which the segment 0 and 1, on which RT is higher, has a higher value for t's in A, then R as the values for t's in the subset 0, 1. Okay, so again, let's do this segment. Here is 0, here is 1, here is a range A, okay, and a part, another disjoint part B, and somehow R is higher on A than it is on B. It will not be in our benefit to actually choose or put x, if x is 1 here and let's say 0 here, it's not going to be for our benefit to change and make R equal to 1 here and 0 here, because R is higher here. Okay, so if I take R and R is here on this range and R is here on this range, no, I don't want this lower return. So I will not switch. If x here is 1 and here is 0, I don't want to switch. Okay? If x is 0 here and it's 0 here, exchanging will not make any difference. So that's not an exchange that will improve anything, because I'm multiplying by 0 the R in both areas. So that's okay. Okay, so that's an exchange argument. The reason why I mentioned the hardy Littlewood poly, yeah, it is possible, especially in the continuous case, but not also in the discrete case, like in the previous 3 videos, to use the hardy Littlewood rearrangement theorem. Okay, so I don't want to rearrange the R basically, or the X, sorry, is how I arrange the values. So I take first, what I take first, I first take the t's for which r is higher, and then I keep going down and until I hit the threshold c, and then I switch the x to be equal to 0. I don't want to rearrange that. Okay, so basically what we can use, or another way to prove all the theorems and why the greedy algorithm is working and giving us the optimal solution, both in the discrete and definitely in the continuous case, we can use this very nice, elegant theorem. It's called the rearrangement theorem by Hardy, Littlewood, and Polya. Okay, thank you for watching.